All right. So, oh yeah, we're recording today. So, now I'm not sure how the week will go here as far as, the plan is for a quiz, but with a snow day on Thursday.
I think it's pretty
Oh, it's gonna happen.
It sure sounds like it. I'll be honest. When it comes to snow days, I'm the pessimist. I mean, I'm the one that always says you just gotta, it's not gonna happen. It'll move south. We're not
That's
gonna
usually
get
what
it.
happens.
And it is usually what happens. And so, but that's just always been kind of my philosophy, is kind of be the pessimist. And that way, if it does
But you're
happen, you're
thinking
happy.
you might think it's not too.
Well, yeah, I mean, if it does happen, you're happy, and if it doesn't happen, you're like, see, I told you. And you're like, yeah, I knew it all along, and so you're not disappointed. That's kind of my theory. So, but this one, it's hard to imagine the way they're talking, because, well, it's usually the timing I know is the key. And, I mean, this one, they're talking about the heaviest band being like 3 a.m. Thursday morning to noon Thursday. I mean, that's pretty much the automatic snow day time. What's that? So, now the good time, the better time frame would be this threat of the heavy, or get enough by 4 in the morning Thursday morning, but then the real heavy stuff not happen till middle of the day, late in the day Thursday,
So we
which
got
could
two.
carry into Friday. But
We're gonna have to
anyway,
do some sweet potato.
you get the sense that teachers like snow days more than students. So anyway, well, that's, because people like to talk about teachers getting the summer off and like a 3-month vacation and stuff, but it's not really a 3-month vacation, so we don't get paid in the summer, right? I mean, so it's not really vacation if you're not
It's
getting
vacation,
paid.
it's not paid vacation.
Right, it's not paid vacation. I mean, in the real world, real people that really work, real
Teachers aren't real. They're the underclass.
when they talk about vacation days, those are paid days. But teachers are on a contract. We have 185 working days, and we get paid for those. And so Christmas is not a vacation. I mean, we don't have to go to work, but we're not getting paid for those days either, right? We only get paid. So our only really paid days off are snow days. That, I think, is what teachers like. Because we don't have to make those up, and those are real paid days. Yes.
It's kind of funny, 'cause last night, we got a call, and my parents thought it was from the school at first, and they're like, oh, it must be Kearney High calling. They're probably gonna cancel school just for the threat of the snow day.
Well, we've done that a few times, but it's hard to know. But my dad was a superintendent when I was growing up, and he had to make that call for snow days, and that was always hard to know. But anyway, oh yeah.
If you think you're not raising as bad in this class, there's Cal 1 class, that's 172 at the beginning and 65 at the end.
173.
173 at the beginning.
And it dropped all the way to 65.
Did you guys hear that? That was James College, or his college visit. They said that was at UNL.
Yeah.
At UNL, the Calc 1 section the kid was in had 170 at the start and 60.
Yes.
So, and my guess is a number of those were ones that went to a school where they took advanced math or something as their last one and then went into calculus. And we've talked about how, this class, as tough as it may seem at times and early on, especially we talk about the pace, and it's really slower than college calculus. So if you come in with just a regular, just kind of advanced math background, whatever, to take college calculus, it can be a real eye-opener. Now, some of you that need calculus, you may decide to go into Calc 1, again, basically be a repeat. And I think I was mentioning to you about a student from last year who was talking about how easy Calc 1 was in college for her. And she's not here. And I was saying, well, it should be, because think about if you took Algebra 2 twice, I would think the second time would be pretty easy, but that'll be fine if that's what you choose to do. We will be talking about the AP test here, about whether you should be taking that or not. And we'll also talk about, should you sign up in college for Calc 2? Should you sign up again for Calc 1 if you need those? Basically, if you have an A in here, you should sign up for Calc 2 for sure, and not take Calc 1. If you have a B, fairly high B, fairly consistently, You know, if you're below that, if you're in the C or whatever, then you probably want to think about Calc 1. And it's whatever you're comfortable with. But if you have, want to know when we get to the end, you make a college visit, and it's mostly in the summer you'd be signing up probably when you make your actual orientation day and that kind of stuff when you sign up for classes. Talk to me and I, by the end of the year I can let you know kind of what happens. But I know like at UNL, UNK, you go down for orientation, usually sit with an advisor, they usually, you talk about your schedule. And if you tell them, hey, I took Calc 1, took AP Calculus High School, even if you didn't take the test, they'll let you sign up. Most places will let you sign up for Calc 2. So anyway, let's get back to what we talked about yesterday. So the plan was for a quiz on either Thursday or Friday. I think we would be ready for Thursday. The only thing that worried me about that a little bit was third block, because I have to leave. I'm only going to be in about 20 or 25 minutes of third block today. So they would be a little behind getting ready by Thursday, but you guys don't care, right? Who cares about that? So I was thinking about.
You're recording this?
Oh yeah, I was ready. My thought was, well, maybe on Friday, but then if we have a snow day on Thursday, then that kind of makes that a little different. So we'll have to talk tomorrow. We'll see how far we get and how we feel about things. I think we've done a lot of what would be on the quiz. This whole thing of the chart and this area function is a big part of what's on it. So I think even if we had a snow day on Thursday, I think we could be ready to do that on Friday, which I almost think would be better than waiting until Monday. But we'll see. We'll talk about it more tomorrow and kind of see where we're at. Make sure we have a plan in place for whatever happens there. So let's review the important components from yesterday. These are the two main things that I would want you to take away for sure from yesterday is this, that area function means the antiderivative of little f. Okay, that is absolutely key. Now the A here is the left endpoint. Okay, and of course the fact that this x is here means that this is some function, usually call it big F or big A. We were using big A because it stood for area, but big F, big G, those are normal function kind of things that we use. And of course, we've already said that big F means antiderivative, so it's not a coincidence that we often use big F for that. But you wouldn't have to. I mean, honestly, we could call this function little g of x, and little g would be the antiderivative of little f. I mean, that could happen. I mean, it doesn't have to be capital for the antiderivative, right? We can call whatever we want. So this thing, and again, the secret is having that x up there as the right endpoint. Because that's what makes it a function. A function is a whole bunch of points. It's a whole bunch of inputs and outputs. And so by having x up in the right endpoint, that means we have a lot of different right endpoints that coincide with a lot of different areas. And those are our inputs and outputs. So it's a function. All right, and then if we move the left endpoint, then that changes the C value. All right, so let's work one of those maybe here real quick, like we had yesterday. So let's say we had big F of x equals the integral from 1 to x of 2t minus 7 dt. And I said to you, write the equation for big F. Write big F. Now, what we did yesterday is, remember problem 21? We went through, drew a picture, and did the whole area thing. But I said, you don't have to do that anymore. You did it on number 29, but you don't have to do it anymore after that. Okay? And so you do not have to do that on this one. You do not have to write out the whole area thing. What can you do? You can simply do the antiderivative. So what's the antiderivative here? Okay, now let's be careful here. You're all wrong. Okay. We raise that up to a 2, divide by 2, but I haven't heard it right yet. No. There you go. X squared minus 7x plus 4. C. Okay, now. Time out a minute. Yes, Tiffany. This one is little f right here. This is little f in here. So big F is the antiderivative of that. And so that's why this is big F. Is the antiderivative. What's that? No. In here. Okay? All right. No, this is good. This is good. Let's go back. Okay? Inside here is little f. This is the area under little f. We call that big F. Right? The area under little f is the antiderivative, which we call big F. So back to this. This in here is, I'm glad you stopped me on that because these are the things we sometimes get confused about. So in there is little f. So to get big F, we want the antiderivative of that. Okay, so that's what we did. But now let's talk about why all of you were saying t instead of x. Why is it x? Well, it's because this is with respect to x, right? And this means this. And remember, this is just a dummy variable that's just a placeholder for the real variable, which is x. Remember what happened when we did our trapezoids. The function was t that we graphed, and it looked like this, but then when we went like this, here was 1 and here was x, and then when we did this area, what ended up being in our area formula? Not t, but it was x, right? It was our area formula ended up having x in it, okay? So that is important. I mean, that's critical, because if you put it in terms of t, it'll be wrong. If this question's on the quiz, which it very well could be, write a formula for this, it's got to be in terms of x. Okay? All right. Now, how do we find the C? We have an initial condition, right? We got a free initial condition right in here. What is that initial condition? Big F of 1 is 0. Big F of 1 is 0. Now, this is another question I've been answering for a lot of people here. Understand that when this is defined as big F of x, that means if I put a 1 right here, that's like putting a 1 right here. And big F of 1 is putting a 1 right there. That's the area from 1 to 1, which of course is always 0. So big F of 1 is 0, which means I can come over here, put a 1 in for x, set it equal to 0. So C is what? 6. So my equation for big F of x would be x squared minus 7x plus 6. X squared minus 7x plus 6. That would be the equation of this. All right? Now, what if I don't write this down, but what if I ask you to do the same thing for this problem right here? Why? Why is it hard? What's hard about that? We can't do the antiderivative of that. We do not know how to do the antiderivative of a chain rule. We don't know how to do the antiderivative of something on the inside. Okay? We can't. Now, we did do it if we had a 2x on the inside. We kicked out a 1/2. You remember that? Now, we haven't done it for a while, but we'll be talking about more in the next day or so. But, so we talked about if you did the derivative inside with the 2 in the inside, you kick out a 2, so when you do the antiderivative, like you kick out a 1/2, right? But if it's an x squared or an x to the 6 or something like that inside, you can't do that antiderivative. So we can't do this. Can't do it. Not yet, anyway. Actually, that one doesn't have an antiderivative. Not all functions have antiderivatives. They all have derivatives, but they don't all have antiderivatives, as we'll learn when we get ready for a gateway test on antiderivatives. You cannot, there is no antiderivative of that. Okay? There isn't one. All right. So I would give you simple ones like this where we could do the antiderivative. All right? If I ask you to do this. All right, so that's one of the things from yesterday. All right, second thing from yesterday that I want you to show you. Since an area function is an antiderivative and the left endpoint determines the c, if we change the left endpoint, all we've done is change the c value. So look up here. I was going to hide this. Don't look. There you go. Okay. All right. So here I have big F and big G. The only difference between them is the c value, right? These are both, big F and big G are both antiderivatives of little f, right? So they're both antiderivatives of the same function. So the only thing different is their c value, because the only thing different about them is their left endpoint. Now, I wanted to remind you of a rule that we talked about yesterday, or not yesterday, last week when we were first doing areas. And that was this rule right here. That if I wanted, now we didn't do it with x's, but hopefully you see that this still makes sense. If I wanted to do the area from 1 to x, wouldn't that be the same as the area from 1 to 4 plus the area from 4 to x? Just picture that in your mind a minute. Does that make sense? The area from 1 to x would be the same as the area from 1 to 4 plus the area from 4 to x. That would be the area from 1 to x, correct? All right, so what's another name for the area from 1 to x? Hint, big F. Okay, it's right there in front of you, right? The integral from 1 to x, another name of that is big F. And the integral from 4 to x, another name for that is big G. And then what could we call this integral from 1 to 4? Well, yes, but isn't that c? Now explain to me why that's c. Why is that a constant? Garrett.
Well, since it's really the same function but on a different.
No.
Because it doesn't involve any variables like x or such, so you can just get a number out.
Yeah, yes.
Because the integral is close between those 2 points.
Yes. Yeah, I think Dylan and Tiffany are basically saying two different ways of saying the same thing. He said there's no variable involved. I think you meant with the 1 and the 4. I mean, there is down here, but the 1 and the 4. And she said it's closed, meaning it's from 1 to 4. It's not a bunch of different right endpoints. It's just what I call a fixed area. This is just a fixed area from 1 to 4. You got the function f up here, little f, fixed piece of area 1 to 4. Like Dylan said, just a number, right? We said that from the beginning with integrals, definite integrals, right? Definite integrals are a fixed piece of area. It's just a number. So this is just a constant. So this is big F. This is big G. This is just a constant. So big F and big G are the same except for some c value. That's what that's saying. So whenever you see this line, and you see it a lot, you see a line that looks like this a lot, all that is saying is that big F and big G are the same except for some added constant. That's what that means. And that's what's true with antiderivatives. Two antiderivatives of the same function are the same except for the vertical shift. That's what we talked about when we were doing a graphing, the vertical shift. Okay. And we'll save that. Okay. So now let's look at the homework questions. Any questions on 3 through 8? And if there's not, you should explain to me why, because I'd be surprised if there's not. Because you asked me about it. Okay? Now, and it's possible you don't, but this is one of those things where you might get the right answer, but you haven't fully thought of all the different possible ways to think about it. I think that's really important. Okay? So, on 3, now I know I did talk with some of you about this. Now, a is defined to be the integral from 0 to x, little f, and this is the little f function here, so this is a of x. So which is larger, A of 1 or A of 5? Now, did we talk about this from a slope perspective and a area perspective? I think we did on this one. So let's talk about number 4. A of 7, A of 10. Which is larger? Let's talk about it from an area standpoint first. What does A of 7 mean from an area standpoint? The area from 0 to 7. I love the fact that some of you just said that right away. Right here, A of 7 means put a 7 right in here for X. Put a 7 right in here for X, which means put a 7 right in here for X. Right? A of 7. I want you just need to see that right away. A of 7 means put a 7 there, which means put a 7 there. It's the area from 0 to 7. What's A of 10? Okay, so area from 0 to 7 would be all of this plus a little piece of negative, right? So mostly positive. Area from 0 to 10, it's going to have more negative added on, so it's actually going to have less area. So A of 7 is larger. Okay, now, forget area. Forget area for a minute. Okay? Now let's just talk about what this means. First slide I put up today. When you see this, what's it mean? Antiderivative of f. What this means, and this is another way you'll sometimes see it, that A prime is equal to f. Wouldn't that be true? If A is the antiderivative of f, then A prime is f. That's what that means. Okay? So that means if we had a chart going on here, we'd have A prime, which would be the same as f. So we had a chart thing. So now let's talk about slope. So now what's bigger? A of 7 or A of 10? Well, let's think about what the A graph would be doing. This graph is the slopes, right? So what's this mean all through here? The A graph is going up until 7, which means at 6 it was going up and it stopped going up. We got a what going on here on the A graph? Local max. Then it started going down a little bit. And then it was like right here. And then what happens? Keeps going down. So the graph decreases from 7 to 10. So A of 7 has to be bigger than A of 10, right? I would like for you to be able to give both of those explanations. You won't have to, but I might specifically ask, is A of 7 bigger than A of 10? Give a slope explanation. Is A of 7 bigger than A of 10? Give an area explanation. I would like for you to do both. So on the one hand, we talked about area. We didn't talk about antiderivative at all. But in the second example, we said, hey, A is the antiderivative of f, and we talked about it as a slope chart kind of thing. Okay? I want you to see both of those. Mostly because I think it's so cool that they both turn out the same. All right. Ooh. Okay. All right. There was another one I wanted to, no, not on that one. Let's go 9 through 14. 11. Okay, now what they told you on 9 through 14 was that big F was what? The area from 0 to x? And what else? And G is 5 to x of little f. And again, the t dt, I mean, as long as it's not x, it doesn't matter what it is, so a lot of times I don't even write it in.
They also tell you that you're supposed to put down the f of t is greater than 1 for all of that.
That is the key, right there. So both of these graphs, both of these antiderivatives, both of these areas under the f graph have to be, you got to know that the little f graph is greater than or equal to 1. That means the outputs of little f have to be up here. And t is greater than or equal to 0, so we won't even be back here. Right, so I don't even need this piece of the graph back here. Yes?
The reason that's important is because theoretically, if the
No, not that so much as some other things. I don't think. Let's see when we get into the problem. So on 11 it says, why, well, let's back up. Number 9, why is big F of 7 bigger than big F of 1? Well, what's big F of 7? It's the area from 0 to 7. See, now, again, I want to approach this. This is a little bit overkill, but I think from the overall concept, I think it's key. Big F, one way to think about it, the area way to think about it, is big F of 7 is the area from 0 to 7. F of 1 is the area from 0 to 1. Well, why does big F of 7 have to be more? There's more area. But why is there more area? Because the area is all positive. Why do we know the area is all positive? Yeah, because little f is above 1. Since little f graph is above 1, all the area is positive, going from left to right. And that's why f of 7 is bigger than f of 1. But what about from a slope explanation? What's little f here from a slope standpoint? Little f is the derivative, right? Big F, big G are the antiderivative. So little f is like the slopes. This is like the f prime graph, right? These are the slopes. It's always positive, so big F is always increasing. See, we give either explanation. Now we get to 9. And 9 says, why is big F of x greater than big F of 0? Well, first of all, what's big F of 0? 0. So what's big F of x? It's the area under this for all x. Well, again, same reasoning really is number 9. Since the area is all positive, big F of x has to be greater than 0. And we know big F of 0 is 0. Okay? So it's that same rationale. But to me, let's talk about 13. And I'd be interested if anybody thought of this. Why is big F of 6, and I know I helped a few people with this, greater than or equal to 6? Let's talk about area. Tiffany.
Okay, well, if it has to be at least 1, that means that from 1 to 6 with just that area, it has to be at least 6, because 6 times 1 would be 6. But we know also that f of t is greater than 1, so we can assume it's at least at some point a little bit above that, so it's probably more than 6, and we can safely say that, but we don't know that for sure.
Yes. So that would be the area explanation. Because big F of 6 is the area from 0 to 6, and since we know the graph's above 1, I'm restating exactly what she said, that there's a piece of area there that is 6 by 1, and we know the little f graph is above that, so this area from 0 to 6 has to be more, I mean, I'd say it has to be greater than, but we could say greater than or equal to, that's fine. And there it is. Now, did anybody think of this as a slope problem?
That's kind of how I thought of it.
Because isn't this the speed limit law? This problem is a speed limit law. From a slope perspective, this is the speed limit law. Because here's what it is. Okay? Let me erase this. Let me erase the area here. Okay? And rewrite this. And now forget area now. Forget area. What we got is big F prime is what? What's big F prime? Little f, right? Big F is the antiderivative of little f, right? We all okay with that? Big F is the antiderivative of little f, okay? So if we were doing a chart, we'd have big F here, we'd have little f right here, right? Okay, and they told me little f is greater than 1. What's that mean? Slopes are greater than 1. Right? Little f is the slopes. So they're telling me the slopes are greater than 1. And now they're going to ask me, okay, is big F of 6 greater than or equal to 6? Well, what I need to know is what is a starting point here? In speed limit law, I always need to know where I started and how fast I was going. Well, here's how fast I'm going. The slopes are greater than 1. Where's my starting point here? What's the point I know? We put it in blue. No, isn't it 0, 0? Remember the free initial condition I get? Right back here? Okay, I'm getting a few blank stares, so look up here. Isn't it true that big F of 0 is 0? right? Because if I put a 0 right here, I get the area from 0 to 0. So if I was going to draw the big F graph right now, okay, if I was going to draw the big F graph right now, it would start at 0, 0. And what do we know about, what does this tell us? Greater than 1. So every time I go over 1, I got to go up at a little more than 1. So what happens if I go over 6?
It has to go up 18 because like.
Not
No, it
18, it
has
has
to
to
go
go up more than
The
6.
volume at 6, like the minimum volume for a triangle at 6 would be.
Whoa, 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 whoa. Whoa, 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 time out. We're not doing anything with area, and certainly not volume. I'm not sure you got volume, you meant area. Okay? We're not doing anything with area. We're just doing antiderivative. Okay? Little f is the slope. The slope has to be 1 or more. So if I'm drawing the big F graph, the big F graph starts at 0, 0, and they're asking me about big F of 6. So that means if I go over 6 and the slope is at least 1, what do I got to do? I got to go up at least 6, but probably more than 6. So therefore, big F of 6 has to be greater than or equal to 6. See how we did that without a mention about area, right? It was just the old speed limit law. Start here, you know the slope has to be at least this much. If you go over, you got to go up at least this much. I would love it if, you know, I wouldn't surprised if you didn't see that the first time here. But now when you see these problems, again, because this means antiderivative. First slide I showed you today. When you see this area function, it means antiderivative. So all the stuff we've learned about the chart and derivatives and antiderivatives we can use. Okay? But I like the fact we talked about it with area. I love what Tiffany said right there as far as that area being 6. Right? And think of it as that area. That's great. Okay? I want you to see that too. All right.
So then,
Yes.
14 now.
Is it possible that G of 10 is 3? G of 10 would be the area from 5 to 10. So if this is 5 and this is 10, that area has to be at least 5, right? That area has to be at least 5. So G of 10 is the area from 5 to 10. That area has to be at least 10. Or excuse me, at least 5, so it couldn't be 3. From a speed limit law situation, what's the point that we know? In the G graph, what's the initial condition we know? G of 5 is 0. So if we were going to draw a G graph, out here at 5, we'd be at 0. If we go over 5 to 10, we got to go up how much? We got to go up at least 5. So G of 10 has got to be at least 5. Can't be 3. So area explanation, slope explanation, both work together, give you the same result. All right. So most of the questions there were about areas. I'm sorry, chart stuff. We talked about it in terms of areas, though, but with this antiderivative idea, we talked about it in terms of that. All right. All right, I want to show you one more thing. Okay. This right here. This is in your homework. I'm going to give you a little hint on this one. Big hint. Okay, so you could write this down, maybe in your homework, where your homework page is going to be for today. What do we go to? 12 after? Right. Okay. Okay, here's the problem right here, 63. And in the directions, you're given this over here. That's the big F of x is the integral from -1 to x. of the same function. Now notice this one has z's in it, this one has t's, it doesn't matter, that's the same function. It's square root of 1 plus the variable to the 4th power. So it's the same function. Okay? It's a function we don't know how to do the antiderivative of. Okay? Because of that t to the 4th inside of a square root. Okay? Cannot do that antiderivative even if we wanted to. Okay? So there's no way for us to find a formula for big F of x here. Okay? We couldn't do it. Now, yeah, okay. The answer to this is just a number, right? Because this is a definite, like Dale and Tiffany were telling us earlier, this is a fixed piece of area. This is not a function. This is a function. The area from -1 to some multiple unknown right endpoints, we get a bunch of different areas. But this is just the fixed piece of area under this function, whatever it is, from -2 to 3. It's a fixed piece of area. It's a constant. It's just a number answer. Now, here's our question. This is really the goal of all this stuff we're doing now, is how are we going to be able to do these? How are we going to be able to find this fixed piece of area, this number? Well, one way is going to be with antiderivatives. Hopefully we all kind of have figured out now that this integral stuff involves an antiderivative somehow, some way. Okay? Now, this happens to be one we can't do the antiderivative of, but it doesn't matter. A lot of them we will be able to do the antiderivative. If we can't do the antiderivative, we'll have to come up with another way. We'll talk about what those ways will look like. But how could we find this? Well, so here's what I'm going to do. I'm going to take this integral right here, number 63. I'm going to split it into 2. Okay? Now, this is something we talked about earlier today. Do you agree that the integral from -2 to 3 would be the same as the integral from -2 to -1 plus the integral from -1 to 3? Go ahead and write that down, and then we'll take a second to look at it. That grid's kind of bottom. Remember we talked about that? The integral from A to B plus the integral from B to C is the whole integral from A to C. Now we said that also works if you go backwards, right? If you're because this is backwards, -2 to -1, right? No, it's not even. No, it's not. -2 to -1, -1. Oh yeah, no, that's even the easy one. But it doesn't matter. If it was flipped around, it wouldn't matter. -2 to -1, -1 to 3. Add that up, you get the area from -2 to 3.
And that makes sense, but how did you pick the -1? Why didn't
Great.
you pick -2 to 1?
Thank you for asking that question, because my next question was going to be, how did I get to -1? Literally, I was just about to say that. How did I get to -1? It comes back to that. It comes back to what I was given, and that's exactly why I picked the -1. So I was given this. Now, again, you are not, in a couple of the homework problems, you're going to mimic this, okay, a little bit here. But it's the result we get from it that is what's going to be important. Okay, it's the result we get from it that's going to be important, not how we did it. But all of the different things we do in it, I hope you understand, because there could be pieces of other problems. So this idea of splitting an integral into these 2 parts is an important concept. Okay, so hopefully everybody understands that. All right, now, let's just take this one over here. What's another name for this right here? We did it on an earlier slide. No, yeah, that's true. This is a number. This is a number that when added together will give us this number. But I'm talking about in terms of this. What's another name for this right here? Big F of 3. Isn't this big F of 3? Which of course is just a number also, right? It's a function big F with a 3 plugged in, right? So it should just be a number. But did everybody see that? That this is big F of 3? Okay? Because -1 to 3 would be like putting a 3 in for that x, which would be like putting a 3 in for that x. So this is big F of 3. How can I make this be big F? Why can't this one be big F? Yeah, the negative one's not in the right place. Is there any way I could get the negative one in the right place here? Can I flip those two and make it negative? Because what happens if you go backwards? It makes it opposite, right? So that's what I'm going to do in my next step, because my goal here, and now you're saying, why was this your goal? Well, that's a fair question. That's okay. You wouldn't know necessarily. I think the directions in the homework is to get to write this integral. The directions were write this integral in terms of big F. So that's how I would know that I want to do this. The directions are write it in terms of big F. So what I'm going to do is I'm going to take this integral and flip it so the -1 is down where I want it to be in my big F equation. And so now this integral is the same as what? F of -2. Negative F of -2, right? Because now the -2 is in the spot where the x goes. Okay, so just a little manipulation here of integrals, which is something we learned in the very first section. So now I'll go ahead and write that. So that first one is negative big F of -2. The second one is big F of 3. And now I'm going to flip those two around. Make it big F of 3 minus big F of -2. And what is that result? That result is this integral, this fixed piece of area, seems to be saying. Now remember, this in here is little f, right? This in here is little f. So what's big F? Antiderivative. I keep coming back to that, and I want to really make sure that's hammered in. Big F is the antiderivative of this function in here. Now, I told you it was one we didn't know how to do the antiderivative, but a lot of them we will be able to. So whatever this function is doesn't matter. It seems to be saying to get this area, all we need to do is the antiderivative of this, plug in a 3, take that same antiderivative, plug in a -2, and subtract them. Isn't that what it seems to be saying? And that will give us this area. Now what about the plus c? Because different left endpoints, if this would have been a 7 here, then I'd had to work this with a 7, but guess what would have happened? It still would have came out to be this, wouldn't it? If I'd have made this be a 7, then this would have been a 7, this would have been a 7, I'd have to flip it, this would have been a 7, everything would have been the same. So why does a plus c not matter? Well, think about it. If you take an antiderivative with a plus c on it and stick in a 3, you'll get something plus c. And then you take that same function plus c, put in a -2, you get another number plus c. Now what happens when you subtract those? Won't the c's cancel out? The c's will just cancel out, because this will have a c, this will have the same c, because it's the same big F. And when you subtract them, the c's will disappear, so it won't matter. It doesn't matter. So that's pretty interesting. That's pretty interesting. Matter of fact, it's so interesting. It's so interesting that is, it's not quite as interesting as what we did yesterday, which we haven't given an official name for, but we will tomorrow. This is called the fundamental theorem of calculus. Wait. Part 2. The other part's more important, so it gets to be part 1. We'll write that up tomorrow. But this is the most useful part of the fundamental theorem. But without part 1, we never could have gotten part 2. Okay. So here's what it says: the fundamental theorem of calculus part 2 says that if you want to do the area, now this is a fixed piece of area, A to B. Notice I can go ahead and put x's in there now because I'm using A and B. They're just numbers. Right? A and B are just constants. So this is a definite integral. This is a fixed piece of area. How do I find the fixed piece of area? I take the antiderivative, plug in a B. I take the antiderivative, plug in an A, and I subtract them. Now,
After 4 months, we'd already have learned the
you
fundamental
would
theorem.
think the fundamental theorem of calculus should come a little early. I would not disagree with that. Okay? Fundamental theorem of calculus.
Hold on,
Now, what's the reason part one, now, it's funny, is in older textbooks, it was actually reversed. This was called part one most often. And I think that's because it's the most useful in like applications and problems that you work. So you probably spend a lot more time using the fundamental theorem, this fundamental theorem. But as far as ideas go and the concepts, which I've really tried to emphasize to you throughout the year, the other part is way more important. But it's more theoretical. So anyway, we'll get into that tomorrow. But so in directions, it says use the fundamental theorem to solve these integrals. They're talking about this one. They're talking about part two, fundamental theorem part two. Okay, so let's do an example. And go ahead and get your calculators out just to test this. But we'll do a simple one where we already know the answer. So let's do the integral from 1 to 3 of 4 dx. I'll show you here in a second. Well, we'll do it for this one. Well, wait, time out. Before you do this one on the calculator, hopefully you don't even have to draw a picture yet on this one. What is this area?
8.
Why is that 8? Horizontal line at 4 from 1 to 3, so it'd be a 2 by 4 rectangle, area of 8. Now, according to the fundamental theorem, part 2, the fundamental theorem says we should be able to do this antiderivative. What's the antiderivative of 4? 4x. Now, I'm going to use a notation here I call the right bracket notation. We'll do more of this tomorrow. But here's how I want to do this f of b, f of a thing. We're going to do the antiderivative, 4x. I'm going to put a right bracket and put a 1 and a 3 on there because I don't want my integral symbol anymore because I've already done the antiderivative, so it's not an integral anymore. I'm not doing the integral of 4x. Okay, the integral was a 4. So I got my antiderivative. Now I'm going to plug in a 3. This is now the f of b minus f of a thing. This is my big F right here. And now I'm going to plug in a 3, right? So big F of 3 would be 12. And then plug in a 1. Look at that. Now, we already talked about how in your calculators, right? Why can't I get my calculator? Okay, so go on your calculator to your scratch pad and go to the template, to the integral thing. Type in 1 to 3. Put in a 4 and a dx. Hit enter, and you get 8. Now, Jake's question is, can this calculator do antiderivatives? Yes. In that same template, get the integral that doesn't, get the integral that's just right next to the integral we just used, the one that doesn't have an a and a b on it. It just has just the integral symbol. If you type in a 4 and then dx and hit enter, it gives you the antiderivative. Now, it leaves off the plus c. Okay, it leaves off the plus c. But that integral without the a and the b on it is basically saying do the antiderivative. Okay, so that's how we can get it to do antiderivative. So watch what happens here. If I would go up here, remember the one I said a minute ago did not have an antiderivative? Square root of 1 plus x to the 4th dx, and I hit enter. Notice how it still has an integral in the answer. Okay, that actually does break out into a little bit of one. Let me change that to one I know does not have any sort of thing you can do to it, and that'd be sine. That one I put up here earlier, x to the 6th power. Okay, and you hit enter, and it just spits it right back out at you. It says, you can't do that. There's nothing to do there. Okay, so it just gives it back to you. All right, so now let's do, a little more challenging one where, let's do this one. Let's do the integral of from 0 to pi of sine x dx. Now, do you remember a homework problem the other day where they just told us what this was? You remember what they said?
I remember doing that pie one, but it was like between, oh, I think it's
No, that was a different one. It said it was 2. We did a problem where it said the integral from 0 to pi of sine x dx is 2. Okay? Now that probably seems reasonable. I mean, this is a height of 1. This is 3.14. So if this was a whole rectangle, it'd be 3.14 times 1, so it'd be an area of 3.14. You take out this piece, take out this piece. 2 would seem reasonable, right? Seem like a reasonable answer for the area. Okay, well now let's do this fundamental theorem thing we just learned. Okay? What do you do? Antiderivative of sine is negative cosine. And we're going to do that from 0 to pi. So this is the f of b minus f of a thing we just learned in problem number 63. And so that's going to be negative cosine of pi minus negative cosine of, now you really need those parentheses, you got to really be careful about those, negative cosine of pi minus negative cosine of 0. Now what's cosine of pi? Cosine of pi is negative, cosine of pi is down here, negative 1, or on the unit circle, pi back here, that's negative 1. So a negative on it would be 1. And then this turns into plus cosine of 0, just like that. Area is 2. And again, if we type this into our calculator, it would spit out an answer of 2. Okay? So this is pretty awesome. I mean, now because of what we learned about the fundamental theorem, meaning integrals, meaning antiderivatives and all that, and then we just showed in problem 63, we showed how that worked out. And then we just said, I think that'll work all the time, and it turns out it does. And so as long as we can do the antiderivative of little f, then this will be a great way to find any piece of area that we couldn't have found before because geometry didn't work on that sine one. We didn't have a formula for under a sine curve. Well, now we do. So this is fundamental theorem part 2. Okay, not really going to do too much of that in your homework. Well, there'll be a little bit of that in the homework today. I'm going to give you the rest of the time here to work on your homework. So we're going to, there's a couple different parts to this. Let's do, kind of changed my mind on what I was going to do here. We're going to do section 5.2. No, we did that already, day 2, right? No, we didn't finish it though. No,
We did the top line instead of ready for day 2.
Right, okay. So 39 through 44 I said I was going to do in class, but we're going to save that for another day. That's just some more chart stuff, so that's okay. So we're going to do the second line of 5.2, which would be 45 through 56. And again, those are chart kinds of questions. 61 through 65, but we already did 63, so you're pretty much, that's going to be your roadmap for on those. Okay, now we'll tell you on 45, the first part of 45 through that, they talk about this function 2 minus absolute value of x. That's just the v graph shifted up. That's on 45 through 50. On 45 through 50, they talk about this function right here. Okay, 2 minus the absolute value of x. So just draw yourself a little sketch of that, and then it's just a bunch of chart questions, basically. Okay, now, on section 5.3, okay, on the next line, section 5.3, we're going to do, let me see here, just a few of those. Let's go 19 through 25. And those are fundamental theorem part 2 problems. Those are big F of B minus big F of A, the kind we just did there at the end. With sine x, 0 pi with the right bracket and finding those areas. So that's what 19 through 25 are. Okay? So really, not too much, but really those things right there encompass a ton of what the quiz would be about. It's got a kind of a chart section, okay, some stuff that would be kind of chart problems with area function means antiderivative, that kind of thing. And then it's got this fundamental theorem part 2 with doing some of that. All right, yes.
Wait, I have a question.
Okay.
Survey.
So